Consider this before viewing Understanding Bridges. Talk about the different bridges where you live. How is each able to support the load that travels over it every day? As you watch the documentary, pay attention to the ways engineers are planning to make longer and more enduring bridges in the future. Assignment Discovery now presents Understanding Bridges.
They are dramatic landmarks. They are the lifelines that bring us together, help us communicate, and provide economic stability. We travel over bridges every day, but rarely give them a second thought. We trust them with our lives and our families and assume they are safe to cross. But sometimes they fail us. This is the story about the ups and downs of bridges. Throughout civilization, people have relied on bridges. We've moved from logs over streams to viaducts that seem to stretch forever. From natural stone arches to the great Roman aqueducts, to graceful spans that leap across space. From primitive rope bridges to our favorite city landmarks. They continue to stretch the limits of technology and imagination. Today, our way of life depends on bridges. In the United States alone, we make at least 3 billion bridge crossings on any given day. That's around 12 crossings per person. We tend to take this for granted until one of our economic lifelines fails. It was rush hour on October 17, 1989. The Loma Prieta earthquake stopped the San Francisco-Oakland Bay Area in its tracks. The earthquake measured 7.1 on the Richter scale. Several bolts on the upper deck of the Bay Bridge simply could not support the enormous force. Within a month of the collapse, engineers at California's Department of Transportation were able to patch this crucial lifeline between San Francisco and Oakland. But years later, they are still dealing with the problems the disaster created. This is not an easy bridge to fix. In the first place, it was not an easy bridge to build. Ever since the gold rush, people dreamed of a link between San Francisco and Oakland. But the distance, depth of water, and soft soil posed enormous problems.
We consider a lot of different things in choosing different bridge types. First of all, the span length. What do you have to cross? The second would be what's underneath, what's supporting it. Is there good material? Can you have the strength to support long spans? The third, though, is really not outside the design realm. It has to do with access. What can the contractor bring to bear? Can he get cranes to the site? Because that will dictate, often, the type of bridge.
Engineers also consider what a bridge has to handle, the traffic, Mother Nature, and the weight of the structure itself. Somehow a bridge must transfer these loads to the ground, and it does so by the constant pushing and pulling on each of its parts. On a beam bridge, weight pressing down on it creates compression along the top and tension along the bottom, transferring the loads to each pier. An arch bridge operates totally in compression, pushing the weight out from the center and down to each end. The ends push the arch together and keep it from spreading apart.
You've got to have very solid foundations, because if once a foundation were to slide or to give, that compression would go away and the bridge would no longer stand. So it's a good type of bridge when you have great soils, great stiff rock to embed in it. A suspension bridge really follows its name. It suspends the load from main cables. Those loads are picked up through the cable and then placed vertically down on the towers. But that only can happen if the cable is fixed at its end. So they develop large cable anchorages.
As incredible as it seems, all of the bridges we cross have evolved from these three designs. These are the kings of the bridge world. The great suspension bridges enable engineers to span distances once thought impossible, conquering nature and captivating those who cross them.
If a bridge is designed well, that elegance of that math, of that science, shows up and triggers something in us that says, gee, that's right, that works perfectly.
New York City. Before the turn of the century, it was already big and booming. Its islands begged for bridges to help cope with the traffic and keep the big city economy growing. When it opened in 1883, the Brooklyn Bridge was the longest suspension bridge the world had ever seen. Its main span of almost 1,600 feet set a new record. Before the days of computers and sophisticated machinery, it was sheer ingenuity, manpower, and daring that got the job done.
In the time that Brooklyn Bridge was built, structures that high, that are 200 feet or so above the water, structures that span that kind of distance were unheard of. It was unthinkable to build anything that big. It was the equivalent of the moonshot of 1969, going back almost 100 years. Steel came into use in the early part of the century, and along came Roebling and came up with a design for steel-cabled bridge.
Engineer John Roebling relied on new techniques that made it possible to bridge greater distances. As foundations to support the massive granite towers, he used pneumatic caissons. 2 airtight timber boxes, half as big as a city block, were sunk to the riverbed and filled with concrete. Roebling devised a method of threading and spinning thousands of miles of cable back and forth between the towers. A traveling wheel, like this one on the Golden Gate Bridge, was used to shuttle individual wires from one end to the other and connect them to the anchorage.
Each wheel carried 2 wires across. But today, there are many wheels and several wires in each wheel, so 6 or 8 wires are carried across. The idea is the same, but the application is speeded up a little bit.
Roebling also introduced slanted cables, known as stays, along with vertical cables that support the deck. They lead from the tower to the roadway to steady it during heavy winds. The idea of cable-stayed bridges started here.
Today, when somebody thinks about adding stability to a bridge, they might do exactly what he did. You'd say, wow, isn't that a modern bridge that you see in Europe or South America where you see cable-stayed bridges? In fact, Roebling thought about that before then, and that gave it stability.
But as suspension bridges became longer, engineers learned one of their biggest lessons from a narrow 2-lane span at the other end of the country. In an attempt to build the ultimate slender suspension bridge, its designer failed to account for a constant 40-mile-an-hour wind. pressure from the wind triggered huge oscillations, as well as an incredible torsional or twisting motion. People who used the bridge were literally getting seasick. They compared it to riding a wave.
Here it goes.
4 months after it opened, the wave crashed.
This Colmenares Bridge is a very classic example of having a very bad shape with regard to wind. Very blunt surfaces, the wind attacks, and it has almost like fluid water moving around the pier, creates eddies, oscillating actions then start, and in this case, threw the bridge into a resonance, which eventually collapsed it, all under very small wind forces.
There was very little stiffness built into the bridge to account for the pressure. The deck could have been wider, the towers could have been thicker, but most of all, engineers ignored aerodynamics. They now design long suspension bridges with horizontal girders that are open along the sides to let the wind pass through. That's the case with New York's Verrazano Narrows, the longest suspension bridge in the United States. It connects Brooklyn to Staten Island. Its main span stretches almost 4,300 feet, roughly the length of 14 football fields. Once a bridge is built, most of us assume that it will just keep standing. But these are finicky structures that demand attention. And some people literally must put their lives on the line. Using the latest climbing gear, Jeff Finn and Richard Hunt rappel from the top of the bridge tower and check each part of the structure on the way down. The climbing team is part of an army of maintenance, repair, and inspection personnel assigned to each bridge. They are well aware of the consequences of missing even the smallest crack. In December 1967, cracks in a single steel eye-bar went undetected. Before long, these flaws brought down the Silver Bridge over the Ohio River in West Virginia. Changes in temperature weakened the eye-bar over time. No one was paying attention.
There were probably micro cracks in the eye bars. Those micro cracks became bigger cracks and caused an immediate failure of the bridge. And those are the kinds of things that might be picked up or should be picked up in inspections, certainly in modern inspections. Nobody can really predict accurately the speed of propagation of a crack. So one day it could be tiny, you come back a month later and it's much larger.
The collapse prompted the federal government to require regular bridge inspections. Now, every 2 years, each bridge over 20 feet long is examined and graded. Most modern bridges are made from a combination of high-strength steel and concrete reinforced with steel bars or threaded with steel cable. Scientists are finding new ways to strengthen them, but even the best man-made materials have limits.
Steel wants to revert back to its natural condition. It wants to corrode. That's its natural tendencies. In the Bay Area, we have a lot of salt in the air. The fog brings in salt, deposits it on the bridges, and you get an accumulation of that over years.
And as soon as that salt and the water and the debris are attached to the steel or somehow pawned on the steel, you get an electrolytic reaction, and the steel itself begins to consume itself. It's like a battery. Part of it's an anode, part of it is a cathode. You can actually measure the electricity on the bridge itself, and you could see that once there establishes a current, you're corroding that bridge. You're transferring steel into rust.
That's where the painters come in. From top to bottom, all year round, painters clean and coat every inch of steel.
One of the best set of eyes on this bridge is the paint crew. We rely very heavily on their expertise. They don't just come out here and slop paint on. They come out here, they look, they see something wrong, they give a call.
They're not the only ones keeping an eye on the bridge. Tow truck drivers patrol the bridge 24 hours a day. Electricians change an average of 2,000 light bulbs a year.
We have steel crew, we have concrete crews, we have carpenters. I'd say over 200 people.
This is what can happen when you turn your back on a bridge. Underneath the Williamsburg Bridge in New York City, mere bandages keep it standing.
We're standing under a 60-foot girder, and that girder should be in a straight line. It should look like the letter I. In fact, if you look at it carefully, it looks like the letter S. It's been struck a number of times. It's been poorly maintained. These wood posts are here, and what we have are wood posts that are supporting a steel bridge because there is no structural support for it.
As the former chief of New York's Traffic Bureau, engineer Sam Schwartz knows all about infrastructure. It's not just the Williamsburg Bridge that concerns him. Every year in the United States, an average of 150 to 200 bridge spans suffer partial or total collapse. Of the more than 500,000 bridges, as many as 1/3 require some sort of strengthening or repair. The total cost to fix these problems exceeds $70 billion.
I think when it comes to bridges, we are our own worst enemy. Bridges have a useful life just like we do. They get aches and pains just like we do. They exhibit many of the same things that we do. If we begin to think of them as human, and that there is a useful life to them, and in the case of some bridges, could be 1,000 years. We are often shortening that life to 50 years or 100 years, and that's unconscionable.
Engineers can use the latest technologies to design a bridge and build it as strong as possible. They can defend it against Mother Nature and take care of it. But sometimes there are accidents beyond anything they can foresee. During a morning commute in May 1980, disaster struck the Tampa Bay area. A freighter was caught in a dense fog and crashed into the southbound lanes of the Sunshine Skyway Bridge. Part of the link connecting St. Petersburg and Bradenton was instantly severed. 6 cars, a truck, and a Greyhound bus plunged into the waters below. 35 people were killed in one of the worst bridge-related accidents the United States had ever seen. In the wake of this tragedy, engineers decided to build a new type of bridge, a modern cable-stayed structure, a close relative of the suspension bridge. On cable-stayed bridges, diagonal cables extend from the tower to carry the deck.
Essentially, the cables pick the load from the girder and then place them on top of the pylon and transmit those down to the ground.
More and more, engineers are opting for cable-stayed spans because they require less material and combine strength with lower costs. In the case of the Sunshine Skyway, they designed the new bridge to prevent future disasters. Engineer John Corvin was part of the design team.
We changed the orientation of the bridge. In the old alignment, the ships would have to actually come and make about a 19-degree turn as they went through the main span. And that led to the possibility that a captain could make a mistake. The second thing, we doubled the span length from 600 to 1,200 feet, again, greatly reducing the fact of a boat hitting one of the piers.
Engineers gave it a curved deck with a clearance of 175 feet to let tall ships pass safely underneath. They surrounded the main piers with rocks and protected them with massive concrete islands called dolphins. Like bumpers in a pinball machine, the dolphins prevent large vessels from actually reaching the columns.
The bridge really has become a symbol of Tampa Bay. You see it all over the place. It's a real marriage of form and function, strength and beauty at the same time. I think the best quote we've ever gotten about the bridge is that it has iconographic power.
With traffic now flowing, engineers are figuring out what comes next. Several dreams are in the works, or at least on the drawing board. In the not-so-distant future, bridges might be smarter. Fiber optic sensors wired in key places would detect the first signs of trouble.
A bridge is smart when it has receptors, wires, fiber optics that are able to monitor the condition of the bridge at any time, so that from a recording facility, which could be a great distance away at a centralized Department of Transportation facility, it could keep track of a current state of bridge.
Look at what happens in your car. You get in your car now, and your car goes through a diagnostic check. All the modern cars have intelligence built into them. We have to make intelligent bridges, intelligent infrastructure that we can then poll, and it can give us back information so we can respond when the bridge has a little tiny ache, rather than wait until it's such a big problem that we have to replace an entire girder.
Stronger bridges made from composite materials could extend the length and overall life of a bridge.
Aside from just improving our current materials into high-performance materials, we're going to see a great introduction of composite materials. The same kind of materials that we see built into stealth fighters or the wings of F-16s. Carbon fibers are extremely strong materials blended with the right matrix of resins and other materials. They won't corrode, they won't crack, and they have great features for long life in bridges. Maybe sometimes 3 times as long as a standard bridge. But right now they're more than 3 times as expensive.
Signature spans that blur the lines between art and engineering are also very costly. And they're controversial. Many engineers say they are overbuilt, wasting money and materials, emphasizing appearance instead of need. But more and more, there is a demand for bridges designed to make a statement. With new technologies, engineers say there is no limit. In the meantime, it's tough to escape the impact bridges seem to have on us.
So it's the soaring, cutting through space and connecting and overcoming obstacles. And the wonder of it all. What holds the bridge up?
What holds a bridge up is engineering. The combination of technical ingenuity, steel and concrete, constant attention, and sometimes a little bit of luck.
Stay tuned. Discussion topics, activities, and resources for understanding bridges are coming up next on Assignment Discovery.
Missed a step.
Okay, that's it.
Woohoo! Whoa!
Now that you've seen Understanding Bridges, talk about this. Engineers must consider numerous factors when designing a bridge. Make a list of the different types of bridges you saw in the program. Then, discuss the strengths and weaknesses of each type and the circumstances in which each design is used. Now try this. Using popsicle sticks, glue, and string, design and build a bridge at least 2 feet long that can hold the weight of a brick. Then compare designs with your classmates to see which is the strongest. Log on to discoveryschool.com for curriculum materials and resources to support Understanding Bridges. To learn more, Assignment Discovery suggests The Reference Guide to Famous Engineering Landmarks of the World by Lawrence H. Berlow.